We're down to 3 more tests. We have 2 today and 1 tomorrow. Today is the direct comparison test and the limit comparison test. These are pretty big deals because we're getting to a place where we're starting to see some functions, some series repeat over and over, and we're becoming more familiar with them. And consequently, we know about their convergence and divergence by any given test. And so the thing that's nice about the test that we're going to look at today is we're going to reference other series that we already know their convergence of or divergence of, and use that to help us figure out the convergence or divergence of new series. So we are, I don't think I wrote the page down. What are we on here? Direct comparison test. 220? 220, I'm going to write that down. I forgot to. Page 220. All right, so here's what's going on with the direct comparison test. We're going to look at 2 different series. And the trick is how the series relate to each other in terms of which one's less than, which one's greater than. But ultimately what happens is, and below this, and he put it in the workbook, but I'm going to give it to you without it for now. If A is less than B, right? It's n terms. This is a sequence A, sequence B. B converges if A converges. So if the smaller one converges, the bigger one converges. Sorry, I said that backwards. If the bigger one converges, the smaller one converges. Divergence can be tested if the opposite. If the smaller one diverges, then the bigger one diverges. And so that's kind of the way think about it, right? If the larger series converges, then everything below it must also converge, okay? And at the same time, if a smaller series diverges, everything above it, bigger than it, must diverge. The trick to this test is keeping this straight. And however you figure out how to keep that straight, that's the critical part. Because we're going to be generally comparing the given series to a series we already know its convergence or divergence of, because we've worked with them in the past. So that's kind of the key. Note the series, the condition is, and it says that in the very first line, let 0 be less than A sub n and B sub n. They have to be positive. The series has to be positive all the time. So we can't use an alternating series. We can't use direct comparison test when it comes to alternating series, right? Because alternating series, every other term is negative. So whenever you see an alternating series, you know you can't use this. It has to be positive. So the trick is, when they give us the series, you want to think of a series that's 1, simpler than what they've given us, and 2, that you may already know the convergence or divergence of, okay? So here's the first, we're going to go through 3 examples, all right? And there's going to be parts of every series that we look at that have familiarity to it. And it's a matter of trying to figure out, what is this familiar to? What is this close to? Because if we can figure that out, then we can make a determination on which way to go with this, all right? All right, so on this first one, how would this be a lot nicer of a sequence, on that formula? What would be, how could we make this nicer? Or what's another fraction that's nicer than this, that's very similar to it? Yes, we still got to have the n in it though. Yeah, so what would be nice is if this 1 plus was gone, right? So what we're going to do, okay, we're going to compare it to 1 over 2 to the n. And the thing that's nice, and here's where, again, your sort of basic arithmetic has to come back into play, right? If the number on the bottom of a fraction is bigger, then the whole fraction is actually smaller, right? Let's think about that again. If the whole number on the bottom is bigger, then the other fraction is actually, that fraction is actually smaller. So our gut instinct when we look at this is to say that this is bigger than this because it's that 1 plus. But because it's in the denominator, this whole fraction actually ends up being smaller. So what we're set up to do is test for convergence. Because if this converges, then this converges. All right. Opposite way too. If this diverges, then this diverges. That's the way you've got to keep it straight. Now, what kind of series is this? Geometric, right? Because what we really want to be doing is thinking of it as 1/2 to the n. Right? That's the other thing that as we work through this more, you're starting to get more familiar with this idea that it sure would be nice if they said 1 to the n over 2 to the n. Well, 1 to the n is just 1. So that's why they don't do it, all right? So what do I know about this series? Why? Why does it converge? What does r equal? And it is less than 1. Okay, so really important to state those things. R equals 1/2, which is less than 1. Therefore, we can determine that it converges by geometric series test. Okay? Well, if the larger one converges, everything smaller than it also converges. So that's really what we're doing here in the direct comparison test. We're actually determining convergence or divergence for a series that is not even in the problem. And because we prove that first, then what we can say is, all right, well, 1 over 1 plus 2 to the n converges by direct comparison. We are directly comparing it to 1 over 2 to the n.
So, why did we do the whole, 0 is less than, but then, I get the inequality, but why did we do 1 over 2 to that?
So the trick to using direct comparison test is to pick a series that is familiar to us, that we can easily determine convergence or divergence of, and then make the rest of it fit into that. That's the whole key to this direct comparison test. Use something simpler than what they give us, that we can easily find out whether it's convergent or divergent, and then go from there. Now, the trick would be, what's going to happen sometimes is you're going to pick something that's bigger, we're going to get to that in a minute, and this is going to diverge. Well, this doesn't mean that this diverges if this diverges. It has to be the other way around. So then you're going to have to potentially experiment with a different fraction, okay, or a different function. Did that answer your question? As we work through this more, you're going to see, okay, pick something that seems familiar and easier to deal with, and then compare it to that, all right? So like the next one. We should all be thinking the same thing here, what we should be trying to compare this to. What should we be trying to compare it to? 1 over n, right? You just kind of eliminate the rest of the numbers. All right, now here's the trick. What do we know about the series 1 over n? Divergent. What is that series? What is the series 1 over n? The harmonic, right? That's the harmonic. P equals 1. It's divergent because of the p-series test. All those things. So, knowing that, we have to ask ourselves the question, because in order for the direct comparison test to work, 1 over n actually has to be smaller than 1 over n minus 2. Because if it's not going to help us. Because for convergency, this one has to be convergent. But for divergence, this one has to be divergent. So there's the question, okay? Is 1 over n smaller than 1 over n minus 2? Okay, so let's
Yes.
I see some solid yeses, I saw a no, and I saw some perplexed looks, okay? Here's my recommendation when you can't figure that out. Test a few values. Pick n1, 2, 3, and just quickly go, okay, which one's bigger, which one's smaller, okay? The caution that I want to give you there is sometimes you can look at the first terms after the fourth term, and it'll work. And it won't work for the first 3 terms or something like that. So just be careful with that. But go back to my original thing we were talking about. Is this n minus 2 bigger or smaller than n? It's smaller, but because it's the denominator, that makes the whole fraction actually bigger. And so that's that number sense that you kind of have to think about. All right? So when we set this up, this is really where we're at. 1 over n is smaller than 1 over n minus 2 most of the time, right? There's going to be sometimes you can pick a value for n where they might be equal. Maybe not. No, they won't be.
You don't have to take another function, you just have to like swap the places in the.
Yeah, you just have to put it in the right place, right? Now, because, as we've already talked about, this diverges, it's the harmonic series by the p-series test. This is the right place to show that this diverges. Okay? It has to be the smaller one. Or if you want to think about it, in the middle, because there's a 0. It's up to you. However you figure out that this one has to diverge for this to diverge, and this one has to converge for this to converge. All right. Anyway, diverged by the p-series test, I'm going to add in here. This is the harmonic. Rather than going through the saying, p equals 1, p-series diverge from when it's 0 to 1. Okay, the harmonic series kind of saves us from having to write all that. So therefore, if that one diverges, this one diverges from a comparison test. Okay.
So you have to write, you have to prove both tests.
Well, you really are proving one test, and then you're saying, oh, because of this, then here's how we can use the direct. The direct comparison test isn't anything other than picking some other fraction or function to determine its convergence or divergence. That's really all it is. Okay? Now, first thoughts on number 3. What are we going to compare it to? What do you think? 1 over n to the 1/2, okay? I would agree. 1 over n to the 1/2. Is 1 over n to the 1/2 bigger or smaller than this? It's one of those. Bigger or smaller? Okay, I'm going to write this down. 1 over n to the 1/2. Okay? Now, it's obvious which one of these what happened there? My 2 went away. Okay? It's obvious which one of these is bigger, right? But if it's in the denominator, that makes this one smaller. So here's my cut for this. Okay, this is where we're at. And so, right, so that whole keeping that stuff straight is so important with this test. What do we know about 1 over n to the 1/2? Convergent or divergent? Convergent or divergent? What does this power have to be between in order to be convergent? This has to be greater than 1. Okay, it's not greater than 1, it's between 0 and 1. So this is divergence. Okay, so here's the thing. This fraction is not going to work. Because in order to test for divergence, this is the one we need to check. The only way we could use a fraction bigger is if it was convergent, which it is not. So this doesn't work. Can't use 1 over n to the 1/2. But I agree with you that we should have tried that. That's the first thing that we should have thought of. All right. So what I need, I still think your gut tells you this is probably divergent, right? This is sort of really close to this, which is divergent. So what I need is a function that's actually smaller than this all the time, or most of the time. See, this is the trick. It doesn't have to be all the time, just most of the time. So my question to you is, would 1 over n work? Is 1 over n smaller than this? And I'm going to write it out. Okay? That's what we're trying to figure out. All right, so we get 1. And then we get 1/2. Not smaller for n equals 1. Okay, let's try 2. 1/2. Plus 1 over root 2 plus 1. Bigger or smaller? Which one's bigger? 1/2 or this? I know you can't read it. Square root of 2 over 1. Which one's bigger? This one's still bigger. Because this is, what, square root of 2 is 1.7 or something like that. So this is 1 over 2.7. So this is smaller. Yeah. All right. So then if I plug 3 in, this is, I'm running out of room, 1/3 over here. But then this one is 1 over the square root of 3 plus 1. Actually, maybe the square root of 3 is 1.7. Which one's bigger, 1/3 or this? But they're getting closer, right? They're getting closer and closer. And so then let's look at one more, because 4 will make this really easy, right? Because if I put 4 in there, the square root of 4 is 2, and now it's 1/3, right? So now it's switched. These were all bigger until we got to here. It might even be here, actually. I would like to know, would you tell me what the square root of 3 plus 1 is? Maybe we're already there.
It's 2.7.
2.7 something, okay? So when n equals 3, this one is smaller. This is bigger. Even though the denominator is bigger, that means the whole fraction is smaller. So what happens is, at the third term, it flips. So the first couple terms it doesn't put it in the right place, but after that it does. So here, long story short. Oh, we already talked about that. Wrong place. Come on. Okay. So when n is greater than or equal to 3, this is true. And you only need a select number. I mean, granted, there's still an infinite number of numbers. But you can rule out the first few terms, because what happens long term is what we're talking about. Because we're talking about as these series approach infinity. So when they get to the end. All right. So this ends up being true. So now we've got it in the right place. And notice we used 1 over n instead, right? Again, a series we know is divergent because it's a harmonic series. And I put it in the right place, which means this is going to be divergent. Once we do that, again, we said the p-series test. We could also say harmonic series. I would refer to the harmonic series when you can. That's why it diverges. So therefore, this also diverges by the, even freezes everything up on me. Like now. Copy. Direct comparison test. Go back to that. This program just likes to auto-save. Paste. Okay. So that's kind of how the direct comparison test works. Get it in the right place for divergency, make it in the middle, make it less than, however you want to think about it. For convergency, make it greater than. Okay. So let me say that again. The smaller one has to diverge to help us, and the bigger one has to converge to help us. Otherwise, we can't use the test. It's not an if and only if. It's a one-directional test. Okay. All right, let's go to limit comparison. Comparison test. So there's some rules here too. So that's sort of the trick to all these tests, right? Is what rules, what conditions must apply for this test, and what am I looking for? So in the limit comparison test, first off, both have to be positive. So again, alternating series test isn't going to be used here. And then you're going to take the limit of the ratio of the two. And if that limit is finite and positive, So in other words, it's going to be any positive number or any rational positive number, maybe is a better way to say that. Then both of those series either converge or diverge. And so in a way, we're going to be doing something similar to what we did with the direct comparison test. We're going to find another series that is much simpler than the one they've given us. And we're going to take the limit of its ratio and see what happens. And most of the time, that other series that we're going to use to compare with, we can easily find whether or not it's convergent or divergent. Here's what's nice about this. This is sort of another, because at some point we're going to have to, they're just going to give us a series, you're going to have to say, is it convergent or divergent? You're going to have to determine which test to use. And at some point, we got to start giving you some clues as to when to use what. So one of the things that they talk about here is that when you're talking about a messy algebraic series, a bunch of different powers, probably not factorable, can't simplify it, it's just kind of an ugly looking thing. Okay? And so what we're going to generally do is set it, compare it to some other easy P series. And the thing that's nice about this is when you're just calculating the limit of some algebraic expression, we only really pay attention to the leading coefficient and the highest degree term anyway. And so that's still going to be our focus. So intuitively, what you already know about limits and algebraic expressions, that idea still exists and you'll be able to apply it. Let's look at some, and I'll explain a little bit better what I mean. All right, so here's 3 more. Right, so these are kind of ugly looking. They're starting to get ugly looking. Now notice here on number 4, the end value starts at 2. Why is that important? Why did they start at 2 instead of 1?
It's not negative.
Right, make sure that it's positive. If this was 1, this would be negative, and then we couldn't use the limit comparison test. Which, again, you're allowed to just think of the rest of the terms and exclude a couple 1, 2, 3 terms, whatever. All right, so what is this? What P series does this look kind of like? 1 over n squared, right? Simplify it down. Disregard the coefficients. Just go with the biggest power. Okay. So they are both positive, as we already mentioned. Well, no, we didn't mention that. 1 over n squared is obviously positive, right? But that's what we're going to compare it to. And so what we're going to do, generally speaking, we use the original, that the original problem ends up being our sort of a sub n, and this one ends up being our b sub n. What do we know about convergence, divergence of 1 over n squared? Convergence, why? Right, 2 is greater than 1, P-series test, we're good to go. So what we're hoping to figure out here is that the limit of the ratio of these two things together, because eventually I'm going to take the limit of this divided by that. And that's what we're doing. We're taking the limit of that divided by that. Well, when I divide by a fraction, we just keep change flip. And so what we set up is just something like this. That's what we're doing. We're taking the limit as n approaches infinity of our original fraction times the reciprocal of the one we're comparing it to that we already know is convergent. What we hope to happen is that this limit will equal a finite positive number. And if it does, then that means number 4 is also convergent limit comparison test. Okay? So, think about this problem. In reality, it's really n squared over 3n squared minus 4. We're taking the limit of that. Well, what is the limit of that? 1/3, right? We don't even have to worry about the 4. We just focus on the leading coefficients of the highest order powers or terms. Well, that's basically n squared over n squared. Those cancel out. It's just 1/3. Okay, simple limits. Right? 1/3 is finite and positive. Okay, we know that 1 over n squared is already convergent. Okay, so we need that. 1 over n squared converges by the T-series test. And, did I write it down? Auto saving again. It didn't, I did not write it down. We should write it down. P equals 2, which is greater than 1. Might as well over-explain it. Really back up our claim. So if that converges, and since we got a limit that was finite and positive, what can we say about the original problem? It also converges by the limit comparison test. I'm going to copy this because I want it to be on the next page. Autosave, how I loathe you. There we go. Okay. Questions about that? All right, let's do another one. What are we thinking here? What are we going to compare to? Just focus on the variables. What is that? What is the square root of n over n? N to negative 1/2, or, remember, we're going to put it in a p-series form. 1 over n to the 1/2. That's what we want to compare to. 1 over n to the 1/2. Which converges or diverges? Diverges. Because 1/2 is less than or equal to 1 and greater than 0. Okay. So we take the limit of all it. Positive still, state that. Again, keep change flip. What do I get now on top? Square root of n times n to the 1/2, what's that? Just n, right? Square root of n times square root of n. So the limit then is, drum roll please. What is it? Oh, thank you. 1. The limit is 1. Is that finite and positive? Sure is. Okay. So then this test is going to work. Okay, we know that by the that as we talked about, 1 over n to the 1/2 diverges because of the p-series test. P equals 1/2, which is less than or equal to 1 and greater than 0. That's the reasoning. I didn't try to squeeze it in there because obviously I'm eating up a lot of space already. That's why I wrote it in there now. I would, you should write it. Okay, when you get to the exam, you should absolutely write it. Again, more justification, more correct justification is going to improve your chances of earning all the points on a free response. So since that diverges, our original problem diverges, limit comparison. Okay. You try the last one yourself. I know you're working on it, but what are you using to compare with? What are you going to use here? What's your comparison?
1 over n.
1 over n squared, absolutely. Ignore all the other terms. Just worry about the leading coefficient and the highest order term. We're just comparing, again, our whole goal is to compare it to a p-series. So 1 over 4 compared to 1 over n squared, which we know that it's convergent because of the p-series test. Just remember to make sure to state that they're both positive. So what is my limit of all of this? 1/4. Positive. Okay, so then we got to say 1 over n squared is convergent or divergent? Convergent because of the test. Okay, and we should be saying that. So p equals 2, which is greater than 1. That's my reasoning. So then our problem also converges because of the limit comparison test. All right.
Does the reasoning just involve P or like the conditions for the P-series test?
Yeah, good question. Do we need to state all the conditions for the p-series test? I think we should, and I probably should have done it too. I'm thinking about it from in terms of what a grader's gonna say.
What other condition do you need?
Is
That
that
P
it's
is
increasing?
Oh.
Yeah, it's increasing, positive, and continuous. Good question. Let me ask about that, because I feel like there's a point where we get, like for the limit comparison test, we're not actually testing the p-series, right? We're using a p-series test. We're using a p-series problem that we already know. I will go onto the Facebook and ask my first question to the group and see what they say. Oh. So I guess the question is this cover that? This is,
That does, because P
but P, no, they're
is
saying,
less than 1.
I'm saying positive, not this.
yeah, it's saying the power is positive. It's not necessarily saying the term is positive, but by saying the term is positive, is that good enough, right? Because if the term is positive, the powers are, I mean, n is positive in all of these problems. So if the power is positive, then the whole thing has to be positive. But there's a lot of inference there, right? So the question is, how explicit do we need to be? I'm gonna find out.
It just says if P is a positive constant. It doesn't say if the whole thing has to be.
Correct, but the limit comparison test says the whole thing has to be positive. That's the rule for the limit comparison test, right? And so it's kind of inferred, right? This, if the power is positive, this whole term has to be positive because the n's are always positive, right? It's when we start throwing minuses in here that we're getting into trouble, right? When they're all plus, yeah, everything's going to be positive because n is always positive. But I'll ask how specific.